Hello, future engineers, and welcome. If you're getting ready for big exams like the TNPSCAE, SSCJE, or even GATE, then you already know just how crucial soil mechanics is. So today, we're going to dig deep into the single most important concept in the entire field, the one that, quite literally, supports everything we build, the bearing capacity of soil.
Okay, so let's think about this for a second. Picture it. You're building a massive skyscraper. You've got the steel frame, the shimmering glass, the whole architectural vision. You might think those are the tough parts, right? But what's the single biggest engineering challenge you're actually going to face?
That's it, right there. The real challenge, the true test for any civil engineer, isn't about looking up at what you've built. No, it's about understanding what's happening deep underground, the ground itself. That's where the real engineering battle is fought and won. Which brings us right into our first section. Look, we're not just talking about dirt here. We're talking about soil as the ultimate test of an engineer's knowledge, their skill, and most importantly, their judgment. You know, this quote is just fundamental. You can have the most beautiful, most brilliant design in the world, but the soil underneath, it doesn't care one bit. It's going to behave according to its own properties. Some soil is strong. We call that superior soil. And some soil, well, it's weak or inferior. And ignoring that difference, that is a straight path to disaster. Now, this whole challenge has a technical name, and it's the central problem we as engineers have to solve. It's the villain of our story, really. It's the bearing capacity problem. And here it is. You need to write this down, you need to memorize it, and you absolutely have to understand it. Bearing capacity is the limit. It is the absolute maximum load per unit area that the soil can handle before it just gives up. This one single value dictates the safety of your entire project. And let's be perfectly clear. If you get this wrong, if you overload a weak soil, the result is total failure. It's that simple. So the load from your building keeps increasing, but the soil down below is weak. Then what happens? Foundation failure. It's as simple and as terrifying as that. Okay, so now that we know the problem, let's break down the two main players in this game. The good guys, the strong, reliable soils, and the bad guys, the weak and problematic ones. This chart just lays it all out, doesn't it? Good, or what we call superior soil, has high strength. It doesn't compress much. It makes for an excellent, stable foundation. And you know what that means? Lower project costs. On the other hand, poor or inferior soil is the total opposite. It's got low strength, it's highly compressible, which makes for a super risky foundation that's going to require way more engineering and way more money to fix. If you're still a bit fuzzy on this, think of it like this. Poor soil is like a soft, squishy sponge. What happens if you put a heavy book on it? It just compresses, right? Now think of good soil as a hard, solid brick. It barely even notices that same weight. So I ask you, which one would you rather build your house on? The choice is pretty obvious. But wait, what if you're stuck with a sponge? What if your job site has nothing but poor soil? Do you just pack up and go home? No way. This is where the engineer becomes the hero. Welcome to what we call the engineer's toolkit, ground improvement. And this right here, this captures the entire mindset of a top engineer. We are not just passive observers of ground conditions. We have the tools and the techniques to actively change the soil's properties. We can literally turn that weak sponge into a strong brick. So how do we do it? Well, it's a systematic four-step process. First up is analysis. We have to know what we're dealing with, so we take samples and run tests. Then comes compaction. For loose soils, we use heavy equipment to basically squeeze the particles together, making the soil denser and stronger. Step 3 is stabilization. This is where we might mix in things like cement or lime, which act like a glue, chemically changing the soil to make it stronger. And finally, step 4 is reinforcement. Think of this like adding rebar to concrete. We add special materials into the soil to give it extra tensile strength and stability. All right, team, let's bring it all home. This final section is all about getting you those marks on exam day. So I need you to listen very closely, because this is the stuff you absolutely have to lock in. Okay, pay attention, because this is where so many students lose easy marks. These are the common traps. First, always check your units. Second, know the difference between dry density and bulk density. They are not the same thing. Third, never ignore the water table. A high water table can completely change a soil's bearing capacity. And finally, understand that compressibility isn't just a word. It's a specific, measurable property. Don't misinterpret it.
So to wrap it all up, when you walk into that exam, these 4 concepts are non-negotiable. You have to have them mastered. Number 1, the definition of bearing capacity. 2, the difference between superior and inferior soils. 3, the whole purpose of ground improvement. And 4, the 2 key properties that drive everything we've talked about: strength and compressibility. That's the foundation of it all.
So I'm going to leave you with this thought. The next time you walk past a construction site, I want you to look at it differently. Don't just see the steel and concrete reaching for the sky. I want you to see the real story, the invisible, silent, and incredibly important battle that the engineers have already won, deep down beneath the ground. You now have the fundamental knowledge of this critical engineering concept. You get the problem, you know the key players, and you understand the solutions. So now it's your turn. Take this knowledge, master it, and go win your battle. All the very best for your exams.